Hello everyone, my name is Maria Stokes, and today I'm giving a presentation on the making of method. This is a comparative study of early optical and gravitational wave astronomy. I utilize knowledge in the fields of physics and history in order to conduct a comparative case study of the early telescope and current gravitational wave detectors. And I do so in order to offer a new analysis on how scientific method actually works in practice. To provide a framework for the investigation I conducted, I want to focus on three familiar figures. Galileo Galilei, pictured on the left, Isaac Newton, who's in the middle, and then finally Albert Einstein. These three men are considered to be three fathers of physics, as well as fathers of modern science as a whole. I want to briefly look at the contributions of these three men. Galileo Galilei conducted early experiments on motion as well as observations through the telescope, and these provided evidence to challenge a geocentric solar system. Isaac Newton formulated laws on motion as well as the universal law of gravitation, building on Galileo's work. And then Albert Einstein proposed the general theory of relativity, in which Isaac Newton's universal law of gravitation was one particular case. When looking at laws, it can be useful to think of them in terms of inductive and deductive thought. Inductive moves from specifics to the laws, and deductive moves from a law down to the specifics or experimental data. These labels, though they can be useful in particular settings, can often obscure what really goes into generating either theory or experimental evidence. And in order to look at this, I want to present a quote from Einstein in regard to Galileo's work, Dialogue Concerning Two Chief World Systems. Quote, "It has been maintained that Galileo became the father of modern science by replacing the speculative deductive method with empirical experimental method. This interpretation would not stand close scrutiny." End quote. My research does exactly that, and it scrutinizes the idea that Galileo purely worked experimentally, as well as the idea that some of these other laws were far more deductive or theoretical than they were. And in order to do that, I will look at two particular cases in astronomy illustrated by instruments. And this is the case because instruments are useful in looking at how astronomy progressed, both experimentally and theoretically. The two instruments that I am concerned with really opened doors in astronomy, both in optical astronomy as well as in a relatively new field, gravitational wave astronomy. So when looking at both of these cases, I will present an introduction of the theories involved before and after the instruments were designed, as well as some of the observations or detections made with the technology. Let's start with the early optical telescope, which I'll refer to from now on simply as case one. Before the invention of the telescope, the prevalent view of the universe was Aristotelian cosmology or natural philosophy. Aristotle, a classical Greek thinker, held that the universe was geocentric and consisted of spheres of varying levels of perfection. These spheres were separated into the superlunary and the sublunary, which were divided by the orbit of the moon. The sublunary consisted of corrupt, perishable, and changeable bodies, while the superlunary was perfect, eternal, and unchangeable. Corrupt bodies were made up of earth, air, fire, and water, and were ordered by their density or rarity. The first major challenge to Aristotelian cosmology was provided in 1543 when Nicholas Copernicus published On the Revolution of Heavenly Spheres. And in this, he proposed a heliocentric system, even though he kept the idea of spherical orbits. The telescope provided evidence to really differentiate between these two postulated theories to determine which one was correct. And the way that it worked was it utilized two lenses, one between the line AB and the other between CD in this sketch made by Galileo. And the lens between AB was a concave objective lens, and the lens at CD was convex. And so these essentially bend light in different ways, and the combination of the two allowed light to be magnified from a faraway source. So this equation here describes how magnification is determined by looking at the focal lengths of the two lenses. And the focal length simply describes how strongly light converges, how strongly a lens converges or diverges light. And the sign denotes whether or not the light converges or diverges. Galileo was able to have magnification of at least 20 with his telescopes, and that's supported by the type of detail he was able to get from in his sketches. We now look at Galileo's observations made with the early optical telescope. In 1610, he published a pamphlet titled Starry Messenger, in which he specified that the moon had spots, gulfs, cavities, and other features. He was able to recognize that this was only because the sun was the source of light for the moon, causing shadows in the craters. He also, in this document, laid out the Galilean moons, which were called by Galileo to be the Medicean stars. These were bodies that orbited Jupiter, and he was drawn to them because they fell on the same plane. He was able to identify that Jupiter was also a center of orbit, not just Earth, as was held in the Aristotelian view of the universe. Galileo went on to look at sunspots, which informed his ideas of motion, as well as the phases of Venus. Venus appeared to change in size as well as illumination as it moved, and Galileo correctly realized that this was because it was orbiting the sun. Galileo's astronomical observations and understandings of motion made heliocentrism conceivable. Furthermore, his observations contributed to the start of optical astronomy. We'll now look at the second case, which was gravitational wave detectors. The theory that was in existence and still continues to describe certain systems before the general theory of relativity was Newton's law of universal gravitation. And what this held was that gravitational force was determined by a constant g, the mass of the two bodies, and then was inversely proportional to the square distance between the two. At the turn of the 20th century, Einstein proposed the general theory of relativity, which holds that gravity is the curve of space-time and is dependent on mass and momentum. So essentially you get curves in space-time around massive bodies. Something that follows from this are gravitational waves, and gravitational waves are carrier waves for gravitational force, and they are transverse and quadrupolar, which means that they contract space-time in one dimension and expand it in the other. This is shown in the diagram where different points in space-time are shown, and they contract and expand accordingly. You have two polarizations which are 45 degrees off from each other. It's important to note from the historical perspective that gravitational waves were not immediately accepted. Einstein actually took back his notion that gravitational waves existed shortly after him and Rosen first published on them, and that was because of their reception by the physics community. It wasn't until Feynman put forward an idea that a few other physicists had been grappling with, which is called the sticky bead argument. And what this says is that two beads on a stick, if a gravitational wave travels through the system, they will expand and contract along this stick. And what's important is that as they expand and contract, the stick remains cohesive because of the bonds internal to it, but you have friction between the bead and the stick. And that implies that there is this introduction of energy, and the only possible source for that was a gravitational wave. And this argument really allows physicists to start thinking about about gravitational waves as direct evidence for gravitational waves has been provided recently using detectors operated by LIGO Virgo. And the way that this works is that light travels down two arms of a detector. These are 3 to 4 mile long arms. And because gravitational waves are transverse and quadrupolar, if a gravitational wave comes through the system, light down one arm will travel a different distance than light on the other. So when they're recombined, it'll show an interference pattern. And that's essentially how gravitational waves are detected. The first direct detection of gravitational waves by LIGO Virgo occurred in 2015 with an inspiraling black hole. You can see the amplitude of the gravitational waves from this event here in this plot. And what's important to note is the strain, 10 to the minus 21. This means that for, given the size of the detectors, they had to be able to measure fluctuations the order of 1,000th of the radius of a proton, which is incredibly small. The second type of event that's been detected are two neutron stars merging. And this is shown by Hubble in the diagram to the right, but gravitational waves from the event were also measured by LIGO Virgo. Both of the events that were measured were from mergers, from binary mergers. But what is of particular significance is that by examining the background of the event, we can gain a more complete picture of the universe at different time periods, as well as more recently, from a summation of the gravitational waves events. This is called the stochastic background. But we can also learn a lot more if we can probe other frequencies in gravitational waves. Now that we have looked at these two cases, we'll return to the task of analyzing the method around them. At first glance, Galileo's work seems to be rather inductive, as he took observations and then those led him to determining the validity of heliocentrism. Conversely, with LIGO Virgo, they took gravitational waves, which followed from the general theory of relativity, and designed an apparatus in order to measure them. However, both of these cases also demonstrate that the inductive and deductive, experimental and theoretical, operate mutually. We see this first with the telescope. Galileo focused in on observations which he was drawn to based on his previous knowledge, which included knowledge of Copernicus. Secondly, with LIGO Virgo, there was little certainty that gravitational wave detectors could reach the necessary precision to actually measure gravitational waves, even though they were motivated by theoretical models. Furthermore, LIGO Virgo data has provided constraints on theoretical models in a more inductive manner. Both the early telescopes and gravitational wave detectors show that accepting a premise catalyzes inquiry, as well as that experimental knowledge further informs theoretical understanding in a symbiotic manner. The statement is quite trivial, but it also emphasizes an interplay between the two. Furthermore, there's a surprising claim that in both of these cases, curiosity plays a significant role. Nobel Prize-winning physicist Peebles wrote that the early investigations of gravitational waves were a case of curiosity-driven research. This is also true for the telescope. Galileo's mathematical instincts proved to be enough motivation to risk a great deal. Similarly with LIGO Virgo, the scientists had to assume that gravitational wave detectors were engineerable. These transition points in the history of astronomy mark moments that later were characterized by theory and evidence, but began with both of these, as well as a certain amount of uncertainty and curiosity. Curiosity-driven research, though not always successful, is quite significant in the history of science. That concludes my presentation. Thank you for listening. I would like to acknowledge support from the Office of Undergraduate Research, as well as thank my mentors, Professor Cagle in the Department of History and Professor Zhao in the Department of Physics at the University of Utah.